Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our thermodynamics discussions. Today we want to look at air compressors. We have talked about compressors. We say that there's equipment which is able to get fluid from low pressure, compress it, deliver it to a high pressure region. Today we want to focus primarily on air compressors. And we want to look at several aspects of it in terms of work, in terms of heat, and we also want to look at the volumetric efficiency of these particular systems. But first of all, let's get a picture in our minds. Let's get our picture in our minds in terms of the pressure volume diagram for the system. Let's get the pressure volume diagram. This particular system. So we have our volume, pressure, then we have, let's call that state point A, state point B, state point C, state point D. Now, we need to understand this diagram because we're going to work with it. We are saying that at this particular point, we have the discharge. Valve closed. At this particular point, discharge open. Here we have the suction open. And we have the suction closed. Now, it's very important to understand some of these concepts which you're going to deal with. So if you draw the full piston cylinder model, remember when we're talking of the piston cylinder model, we have our piston, that's the cylinder wall. We have our piston, we have our clearance volume, we have our piston. Of course, it should be perfectly fitting. There's no space there. Be perfectly fitting as much as possible. Our rod. We have the PDC. We have the TDC. This we have talked about. Stroke. Piston stroke. We have talked about this significantly and substantially. And so we have that picture. We have that picture of what a piston cylinder model averagely looks like. Now, when we have this image of the piston cylinder there, we have some terms which we need to know. So that this volume here, this volume here, we refer to it as the swept volume. That is that volume, the piston moves up or down, that volume it covers, traverses that volume, which is you have that has length, then you have the surface area of the piston, that's A, that volume which it traverses, that's V is equals to AL, that is the swept volume. And that's what we're indicating there. And then we have the induced volume. Induced volume corresponds induced volume. So I want you to have those in mind. So that when I'm talking of swept volume, you know what you're talking about induced volume, you know what you're talking about, because you'll want it when we come to volumetric efficiency of the system. Now, let us move on. The pistons. Now you're familiar with most of these things. In many of the lectures we have covered so far, we have gone over this with polyprotic processes, gone about over the calculation of machine cycles, heat, mass transfer, and many other things. So I'm just requesting you to kindly go through some of those lectures, listen to them so that you are kept informed in terms of. And I also need to just mention that sometimes you might see wavy lines here. I see wavy lines here. Those are malfunctioning valves. Kind of valves kind of throttling. So you might see that might not be perfectly as you see them, but that's malfunctioning valves. There's a symmetry in terms of their opening and the way they release their contents. Now, we know for polytropic processes, the W is equals to MFN1 minus N into P2 V2 minus P1 V1. We have derived this expression in all those circles we have worked with. We have gone through it, and I encourage you to go through those earlier lectures. Now, we have this as our system. So, working with this particular equation, which is for a polytropic process, remember that's for a polytropic process, and you say that for polytropic processes, P1V1 N is equals to P2 V1 V2 N is equals to PVN for polytropic processes. Now, if we reorganize this particular expression, then we see that if we divide throughout by P1 V1, we'll have M N 1 minus N P2 V2 over P1 V1 minus 1. All these quantities remain as you have already defined in all those many lectures, and now you are familiar and used to them. Now, we have this quantity here, but if this is a polytropic process, then what does that mean? We can actually replace this quantity here with pressure so that you have the expression of work that this particular system in terms of pressure. That is, we have, if we have P1 V1N is equals to P2 V2N, then if we rearrange this expression, because we have V2 over V1, then we can have P1 over P2 is equals to V2N over V1N. And of course, we can factor out these exponents so that we have P1 over P2 as being equal to V2 over V1 raised to power n. Now, we just use the simple identity here because I want to bring in the pressure to the system and move the volume. We just use the identity A over M raised to power V is equals to Y over X. Implies that A to the power M equals to Y over X to the power 1 over V. Remember, this is to power 1, so just divide it by V, both sides. That's what I'll do here. So that P1 over P2, the power 1 over N is equals to V2 over V1. So if I bring this quantity here, plug it into that particular equation, then W, and we clearly see that W over P1 V1. In fact, now I can sort out the P1 V1 MF N 1 minus N P1 V1 into P2 P1 into P1 over P2 power 1 over N minus 1. What does that become? It does come this way, because we need to use that diagram. Does it become? Very simple. We still have to sort out ourselves. So we have P1, P2, P1, P1, P2. So we want to configure them so that we can multiply the P2s and we can multiply the P1s. And that's a very simple rearrangement. So W will be equal to MF N1 minus N P1 V1 into P2 over P1 into P2 over P1 minus 1 over N minus 1. Makes our life very easy. Now, just using the identity a to the power m times a to the power n equals am plus n, we can apply that to sort out this. So what do we have there? We have W therefore is equals to m fn into 1 minus n into P1 V1, that is P2, 1 minus 1, we have 1 minus 1 over n, so n, factor that out, so we have n minus 1. So we have P2, P1, n minus 1, minus 1. But suppose now we assume, remember that is work. Remember that is work in the system. Look at it in terms of pressure, and we're talking about polytropic process. Suppose now we assume that we are dealing with an ideal gas. Assume that the air is behaving as an ideal gas. What does that mean? It means that it obeys the characteristic equation for ideal gas, or equation of state, PV is equals to nRT. Now, we say that W was equals to MF N1 minus N into P2 V2 minus P1 V1. So if we assume that this air is behaving like an ideal gas, so it obeys the characteristic equation PV is equals to nRT, then you can see that if I talk of unit amount, so that PV is equals to RT, then you can see that W will be M1 minus N RT2 minus RT1. They just assume it is behaving like an ideal gas. And so, what does this mean to us? What does this mean in terms of what we want? If we go back to our first law for steady-state flow processes, remember, first law, steady-state flow process, we had first law of thermodynamics for steady-state flow process. We say that DH, remember DH, you can look at our lecture on steady-state flow processes, first law of thermodynamics, derivation. Again, I encourage you to do that. DH, dc squared over 2, where c is velocity, and then we have d dz is equals to dq plus or minus dw. Remember, this is kinetic energy. Remember, that is potential energy. And since these are not significant and the datum level is not changed significantly, we can assume that they are both 0. So that dH is equals to dq plus dw. dH is equals to dq plus dw. So if we use this expression here into that particular equation, then we are seeing that m of dH will be dq plus dw. And so that from state 1, 2, then we can say that is m into H2, H1, that's the enthalpy, is Q plus W. So we have our W already for this polytropic process, so that M H2 minus H1 is equals to Q plus MF n to 1 minus N P2 V2 minus P RT2 minus RT1. As I've already always repeated, this plus or minus is a notation. Always remember that. In certain cases, somebody can think of minus W as being work done by the system on the surrounding, or plus W as work done by the system on the surrounding. What is the work done by system on the surrounding means there's a change, that of a weight somewhere in the surroundings. Or if the other way around, is there's a lowering of some weight to load somewhere in the surroundings. So that's a relative term. You can choose minus W plus W. So I don't put too much emphasis on that sign in my books involving thermodynamics. Now, we have MFN, 1 minus that, RT2 plus that. So Q, in a nutshell, is M, H2, H1, H2, H1, plus minus MFN, 1 minus N into RT2 minus RT1. But what is DH? DH we know is related to heat capacity. DH, when we talk of DH, DT, we have that as isobaric heat capacity at a constant temperature. So that basically DH there, we can replace it with the expression for heat capacity. It comes M delta T, which is T2 minus T1, plus minus MF N, 1 minus N into R T2 minus TR T1. Now, if you remember or recollect from our lecture on adiabatic reversible processes, I also suggest that you look at that discussion, adiabatic reversible processes. Let's make sure you look at that. We had this assumption where we say that gamma minus 1 was equals to 1 over C. And this C was CV over NR. And what was gamma? Gamma was the ratio of the heat capacities CP over CV. So what does that mean? It means that gamma minus 1 is equals to NR over CV. NR over CV was 1 over C. And so let's deal with unit amount just like we did. Gamma minus 1, therefore, is equals to R over CV, which implies that R is equals to CV into gamma minus 1. And so we can use in place of R that expression there, so that Q is M CP into T2 minus T1 minus M N 1 minus N R T2 minus T1. So we can factor out, see, T2 minus T1, the change in temperature is common on both sides. So we have Q is equals to T2 minus T1 into MCP minus MFN 1 minus N minus N. We want R. Factor that out. You just remove the T2, bring it out. So we have M, CP, that Correct? So we proceed. Q, therefore, is equals to T2 minus T1 into mCp minus mFn 1 minus n into CV gamma minus 1. Always remember that. CV gamma minus 1. But if you want to unify all of them, remember they're saying that this fluid air behaves like an ideal gas, behaves like an ideal gas, just remind yourself, where we have H, the enthalpy is equals to U plus PV, then DH, the change in enthalpy is DU plus PdV plus VdP. And from first law of thermodynamics for closed system, you know that du is equals to dq plus dw, which is basically dq minus pdv. So if you plug in this quantity here, you have dh is equals to dq minus pdv plus vdp plus minus pdv. We have du is dq minus pdv plus pdv plus vdp. This is the general expression which you get for H, the change in enthalpy, VDP, the change in enthalpy, general. But suppose we now bring in that element, that fluid, that's air, is actually ideal. Then it is no longer the same. It simplifies to something else. So that if we now assume that the air is ideal, now we have H is equals to U plus PV. In place of PV, we put nRT. So that dH now will be du plus nRdt. Of course, if you divide throughout by dt, then you will have du dt plus nR. And so this is, of course, the isobaric heat capacity. This is the isochoric heat capacity for unit amount plus R, so that Cp minus Cv is equals to R. It's always a very important relationship to remember for ideal systems. So what does that mean? Simply means that Cv minus Cv is equals to R minus Cp, or Cv is equals to Cp minus R. So I can plug that in there. And plug that in that particular unit quantity here. Let's say, so Q, therefore, is equals to T2 minus T1 into M, what is M? You have MCP minus MFN1 minus N into Cp minus R, into gamma minus 1. And of course, we now have it exclusively in terms of the heat capacities, isobaric heat capacities. Or you can also just work with it in that form where you have it with the isochoric heat capacity. Now, how do you compute the efficiency of this particular process? How do you compute the efficiency of this particular process? Efficiency of this particular process. Let's just call the isothermal efficiency. That isothermal efficiency is isothermal work over indicated work. But this is fraught with a lot of uncertainties, in terms of even the simple fact that in our system there, remember, for the polytropic process, the dV, V to power n, non-polytropic process where again work is done, dV over V. That brings a symmetry in terms of the mathematical expressions which you get in terms of these formulas. And then we have the issues of friction, and we also have the issues of the valves and so forth. So this isothermal work is normally not probably the most preferred method to establish the efficiency of this particular system, because there are a lot of possibilities of inaccuracy based on elements in the behavior of the system. So it is probably preferable to use volumetric efficiency. And in volumetric efficiency, it will be the induced volume over the swept volume. And you have already shown you what induced volume is and what the swept volume is. So, if we look at our system, what is the induced volume? This is the induced volume. That is from Vc minus volume at state point C minus the volume at state point D. Simply volume at state point C minus volume at state point D divided by the swept volume. Let's call it Vs. The swept volume, let's call it Vs. But also in terms, just the same expression as we move on with it. I think we can clear that now. I think everybody is familiar with it. If you look at this particular system, we have the swept volume and the induced volume. And you notice that the induced volume is the difference of this quantity and the swept volume. So these quantities correspond to the volumes at state point D and at state point A. So we can have that as volume at state point D minus is actually the induced volume is the swept volume minus this volume element, which is minus volume at D minus volume at state point A. That will give you the induced volume divided by Vs. So we can simplify it further if we have, so we have Vs over Vs minus Vd minus Va, those are volumes, specific volumes, and so that is 1 minus Vd over Vs minus, that is now minus Va over Vs, which you can actually write as Va over Vd, Vd over Vs. So now this is just a cyclic notation. This is a cyclic notation, like when you are deriving expressions for isobaric coefficient of thermal expansion and isothermal compressibility. When we derive that, we talked of the permuter, which you could use as a mathematical identity on those partial derivatives, and it was cyclic. I told you can cancel it in your mind. Look at the lectures on those quantities. You will find we talked about the cyclic. So what is cyclic? You can cancel in your mind. If you cancel in your mind, you are left with Va over Vs, Va over Vs. So what do we have? Now we don't need this anymore. So we can use this end. So we are saying, therefore, that the volumetric efficiency is 1 minus Vds, Vd over Vs, minus plus Va over Vd, Vd over Vs. And clearly you can see that you can factorize out Vd over Vs, so that N volumetric is 1 minus Vd over Vs into 1 plus VA. Remember, that is minus VD of VS. So we have minus, so it should be minus VD of VS. Then here is plus, so we need to have minus there. Minus VA over VD. So that is an expression for the efficiency of the system based on the volumes in this particular unit. So I think after all this series of lectures, we've looked at compressors, we've looked at machine cycles. Now I think we are very much in good understanding of some of these things, because now we are familiar with them. We are now familiar with them, and you can do them. They are right at your fingertips. So we are continuing with our thermodynamic lectures. I continue encouraging you to log in and see those other lectures so that you keep pace with us. Thank you.